Everything around us is made up of atoms, but it's hard to imagine just how tiny atoms are. One sheet of paper is roughly half a million atoms thick. Volume wise, one atom is as small compared to an apple as that apple is to the entire earth. So you might be surprised to learn that scientists can actually see atoms. Well, not with their eyes, but with incredibly precise tools. The idea of atoms dates back to the ancient India and Greece, when the philosophers like Rishi Kanad or Democritus declared that all matter is made of tiny particles. The first modern evidence for atoms appeared in the early 1800s, when the British chemist John Dalton discovered that chemicals always contain whole number ratios of elements. The reason for these whole numbers, as Dalton suggested, was because atoms are indestructible. It's hard to imagine chemistry today without Dalton's insight. But it did not take much time for Dalton's idea to crumble. Thomson's discovery of electrons proved that atoms are made up of smaller particles. Rutherford's experiment in the following years proved the existence of positively charged nucleus, which resulted into the discovery of protons and neutrons. These discoveries came with their own sets of prediction about how an atom looks like. But after quantum mechanics came into existence, the picture of atom became clearer, or should I say fuzzier. According to quantum mechanics, the particles can be represented by the probability density because we cannot pinpoint the position and the momentum of a particle at the same time. But how can we see such smaller and fuzzier objects? An obvious answer might be microscope. But to see something under a microscope, the wavelength of light shining onto it has to be roughly the same size as whatever we are looking at. Unfortunately, visible light is thousands of times bigger than atoms. So scientists use light with shorter wavelengths like X-rays. Today we are familiar with the X-rays as a tool in medical science. But scientists don't use X-rays to see through things. Instead, they bounce X-rays off things like crystals, which are solids with layers of atoms. When X-rays hit an atom in a crystal, they bounce back. Others slip through and bounce off the second layer or the third layer or deeper. After being reflected, these X-rays strike a detector screen, and based on where the X-rays came from and how they are interacted with each other, scientists can work backward and figure out the arrangement of atoms in that crystal. This reflection and interaction is called X-ray diffraction, also known as X-ray crystallography. But to have more detailed images, electron microscopes came into existence in the 1930s. It uses a high voltage electron beam to illuminate the specimen and create an image. The electron beam produced by an electron gun is accelerated and focused before transmitting through the specimen. Some parts of the specimen are transparent to electrons and others scatter them out of the beam. When it emerges from the specimen, the electron beam carries information about the structure of the specimen that is magnified by the objective lens system of the microscope. But these microscopes still did not have high enough resolution to capture every atom. They relied a lot on computers to fill in the blanks. In order to look at an individual atom, two physicists named Binnig and Rohrer invented the scanning tunneling microscope. Rather than bouncing light off something, an STM runs a sharp conducting tip that can distinguish features smaller than 0.1 nanometer with a 0.01 nanometer resolution. It's like a sensitive braille, except the tip never quite touches. STM is based on the concept of quantum tunneling. Quantum tunneling is a phenomenon that happens because atoms are strange. As mentioned earlier, they do not look anything like the classical model. In fact, they are not even solid particles at all. They are made of little nuclei surrounded by electrons. But those electrons do not follow nice neat orbits. The most we can say is that an electron has a certain probability of being somewhere at a given time. There is even some probability of electrons jumping from one location to another, and that jump is called quantum tunneling. Particles attempting to travel across a potential barrier can be compared to a ball trying to roll over a hill. Quantum mechanics and classical mechanics differ in their treatment of this scenario. Classical mechanics predicts that particles that do not have enough energy to classically surmount a barrier cannot reach to the other side. Thus, a ball without sufficient energy to surmount the hill would roll back down. A ball that lacks the energy to penetrate a wall bounces back. In quantum mechanics, these particles can, with a small probability, tunnel to the other side, crossing the barrier. This behavior is used in scanning tunneling microscope. When the tip is brought very near to the surface to be examined, a bias voltage applied between the two allows electrons to tunnel through the vacuum. The resulting tunneling current is a function of the tip position, applied voltage, and the local density of states of the sample. As the tip moves along the surface, scientists can reconstruct the atomic landscape, making individual atoms visible. In the recent years, scientists are using different methods to look at the atoms. David Nadlinger captured the picture of a single atom of strontium in an ion trap through the window of a vacuum chamber in an Oxford University lab in 2018. In this year, David Muller and his colleagues at Cornell University captured the most detailed picture of atoms using a praseodymium orthoscanded crystal. They used a technique called ptychography, in which they used an electron microscope to analyze the crystal by calculating the angles of scattered electrons to work out the shape of the atoms that scattered them. Looking at the tiniest building blocks of nature is fascinating in its own way, but it has its own sets of applications too. Just a few years after the STM was invented, IBM began using it not only to look at atoms but to manipulate them. By holding the tip of the needle close to an atom, they were able to use the attraction between the two surfaces to pick up an atom and move it to a new position. The ability to do that opened up a new field called nanoscale engineering, which is all about constructing and researching structures on the scale of molecules. In microbiology research, they can not only take images but also videos of atomic and molecular movement. These scientists have been able to record video of individual molecules coming together to form a blood clot. Being able to witness events like this gives scientists incredible insight into complex interactions. It may also help engineers to create new technology for data storage, which is a constant challenge these days. Instead of relying on conventional hard drives, which store information in magnets representing a 1 or a 0, researchers hope to magnetize individual atoms, which might make it possible to store information at an atomic level. Understanding the interaction on an atomic level might help greatly in quantum computing, where the stability and the efficiency of qubits are important. So in a nutshell, to solve the big problems in science and technology, we need to be closer to our tiniest friends. Thanks for watching. I hope you liked it. Please like and share this video, and to see such videos in future, do subscribe.